Hey everybody! In last week's video, we explored the use of matrices in R programs and saw how we can manipulate and create them to represent more complex datasets than those we had seen with our vectors. In today's video, we're going to explore two different two-dimensional objects called data frames and lists. Data frames are similar to matrices in that they're able to hold only one data type within their columns. However, what makes data frames unique is that different columns can be of a different data type. Lists, on the other hand, allows you to gather a variety of objects in an ordered manner, from vectors and matrices to data frames and even other lists. This is an important feature to have for a data analysis language like R, because data from the real world is a combination of different types. For example, if we were to publish a survey and collect responses from a set population, we employ various data types in the questions that we will ask, from using numerics to collect population numbers, characters to create categories and collect respondents' opinions, and logicals to ask binary-based questions, like having only yes or no options. Therefore, it's important to know how to use and create data frames and lists within our R programs to be able to handle such complicated and nuanced real-world data. For our project, we'll be using data based on the information collected by the Census Bureau in 2019 regarding STEM and STEM-related occupations, organized by respondent sex and median earnings. But before we can use such data, we first have to go through the process of cleaning our data to access what we specifically want. Data cleaning is the process of modifying data to ensure that it is free of irrelevant, incomplete, and/or incorrect information. It's important to go through this process of data cleansing, even though it can be manually intensive, since it's very valuable in improving the efficiency of the results of data analysis. If we were to work with our raw data directly, then the process of data analysis will be much more cumbersome and confusing. Raw data is the data that is collected directly from the data source, such as the Excel sheet shared by the U.S. Census Bureau. We process our raw data through data cleaning to get our desired results. We're going to go through the process of data cleaning to show the steps it entails and how we prepare it for our use in our program later on. First, we will download the Excel file from the following link, available in the video description and on askthecat.org. Now from here, we're going to remove unwanted or irrelevant observations. It's always a good idea to make sure that such changes are on a copy of the original dataset so that we can always have the raw data available in case we made mistakes while data cleaning. Note that I am using a Mac and I have a Microsoft Excel subscription from college, but you can always do these same steps using Apple's pre-downloaded Numbers application or Google Sheets with your Google account. For the sake of today's program, we are not going to include differences in median earnings nor additional statistics like margins of errors and percent values. We only want the total estimated values of individuals employed in each occupation. Likewise, we do not care for the total number of STEM and STEM-related occupations, as we can calculate such values ourselves through our program, which we will see being done in future videos. We can remove additional descriptive phrases and notes that were added to the Excel file so that our program does not get confused and think that this information is also part of the data. These notes, however, are still important for us as a programmer to further understand how this data was collected and how the original researchers categorized such information. Next, we are going to fix the data structure. Right now, our data is in the form of an Excel sheet, hence why we are manipulating such data in a Microsoft Excel environment. However, for our R program, we will use a .csv, or comma-separated value format, to manipulate our data. CSV files allow our data to be separated on commas, instead of reading it in the form of tables and columns like we're used to. This is easier for our software programs to manipulate and edit. To save our file as a CSV, we go to File, Save As, and change the type from Excel to CSV. Now we have a CSV version of the file on our computer. However, when we try to see what the CSV file looks like, we notice two main things. First, the category of occupations is shown right alongside their subtypes, rather than be separated from the specific jobs. Likewise, the titles of each column are clunky and not concise enough to provide useful information about what data is stored inside there. Therefore, we're going to have to fix our data structure by having a separated column for our occupation categories that puts each job into a separate type. Additionally, we're going to rename our columns like so to make the data easily accessible for us and for our computer program. We're also only going to be focusing on the mathematical sciences, life sciences, and physical science occupations to be able to also hard-code such data in our program later on. Now that we made these changes to our CSV file, we have to export it again and make sure these changes are being made onto the CSV. Since I'm using a Mac, my computer automatically opens the CSV in Numbers, but if I do not save it as a CSV again, then the changes are going to be written into a Pages file instead. Now we can use the CSV file for our own R program. When we open our RStudio workspace, we're going to go to the Files tab and upload our CSV file. Now in the Files tab, we will see the CSV file accessible from our RStudio workspace. In our console, we're going to convert our CSV into a data frame that we can use in our program. To do so, we use the read.csv function like so, and assign the result to a variable called jobs_df1, df referring to data frame. It's important to make sure the name we set equal to the file has the exact same spelling and capitalization as the name of the file that we uploaded. Now if we call on jobs_df1, we see all the data that we had manually cleaned easily accessible and readable by our computer program. But let's say that you didn't want to go through that process of cleaning our original dataset and you wanted to hard-code such information into your own program. You can always create your own data frame using the data.frame function and input the respective data types that represent your raw data. For example, we can create vectors of different data types to represent each column of our original data, from the occupation categories to the jobs themselves and the number of people employed in each job. Note, though, that for the occupation category, we are repeating terms because different jobs can have the same occupation. After creating these vectors, we can now input it to our data frame like so. Now if we call jobs_df2, we see that we have the exact same data frame as we created previously. Either way of processing data and creating your data frames is completely valid. It's just up to you as the programmer how you prefer to do so. When outputting our data frames as such, we said there's a larger amount of information that we had to deal with than we had saw with our smaller vectors and matrices. To get a smaller snapshot of what exists within our data frames, we can use the functions head and tail to print out the first observations and last observations of our data frame respectively. Both of these functions print a top line called a header, which showcases the names of the different variables that are stored within our data frame. To get a more detailed overview of the information in our data frame, we can use the structure function, which, as the name states, shows the structure of your data, such as the total number of observations, the total number of variables, the different variable names, the data types of each variable, and the beginning observations. As we saw with vectors and matrices, we can always use the same names of the columns or the number position and the respective row of an element to call on it in a data frame, like so. On the other hand, if you just wanted a certain group of elements from your data, you can find them like so, using a colon to specify the range of elements you're selecting for. If you want to get the whole column of a data frame to print, there are multiple ways to do so, either calling on the column number or the column name, or using the dollar symbol with the name for the column as shown here. But let's say we only want to look at a part of a data frame and to see if it fulfills some given condition. We can use the subset function to select a certain subset of information in your data based on the condition you specified within it. For example, let's say we only want to look at the jobs within our data frame that have more than 100,000 employees. We can specify a condition within a subset to select data only if total is greater than 100,000. What we get is the jobs whose total fits this condition. This is a super cool function because we do not have to create an entire function ourselves to look through all of our data and test this condition. Instead, a built-in data analysis function like this can provide all the necessary information we need to learn more and analyze our larger data frames. Now that we understand how data frames work and how to create them, we can combine our previous discussions on vectors and matrices to use all of these data types for our R programming lists. To create a list, use the list function, and you can define it like so. Note how we were able to store our example vectors, matrices, and data frames within this list, and that these definitions are based on the skills we had covered in all of our previous videos. To differentiate between all the parts of your list, you can name the different components as follows, using equal signs to specify what the name of the component is, and naming in the order that these data types are presented in your list. This first order shows the names being assigned while the list is being created. If you want to name your lists after you've created them, you can use the names function, as we had done with naming our vectors. Both forms of naming will lead to the exact same result. To select an element out of a list, we have to use double brackets instead of single, due to the large number and diversity of components that are stored within our lists. For example, to only look at our vector component of our example list, we would have to call it like so, using the number 1 index since the vector is the first component of our list. You can also refer to the names of the components with double brackets, or with a $sign. Both will select the data frames representing those components. To select specific elements out of these components, you use a single pair of brackets after the double pair. For example, if you want the second element of the vector in the list, we use double brackets 1 and single brackets 2. The following are the other ways we can call in specific elements of our matrix and data frames that are stored within our list. Feel free to test and troubleshoot these other ways to call on your components and elements within your own lists. I hope this video helped you to learn more about the data cleaning process, using such process data to create data frames, and building on such data frames to fill in lists. Next week, we'll be using more of the data provided by the U.S. Census Bureau to try out tools from the Tidyverse toolkit and prepare us for future data visualization.